We'll start with a recap of equilibrium as far as we've done it, and because I can't quite remember myself how far we got, and we'll just move on gradually, you know, in the logical sort of order of things that I've got, and problems and examples and that sort of thing, and see how far we get to. I think we're not in too much of a rush on anything. I think, you know, although time-wise, we know that at this point in the year, it's not unusual to have to rearrange some sessions, but we don't usually have to rearrange as many as we've had to do this year. For anybody who hasn't looked, the plan for rearranged sessions is on Moodle. It's under the general information, and all the rearranged sessions, whether they're from GCSE exams or yesterday or, you know, all this bit, they're all on there. I had to plan the whole thing out. I need to print it off, I think, and stick it on the wall, but we're not pressured for time because we will start finishing stuff in the same way. I think you're pretty much finished on maths, a lot of you, aren't you? Although, you know, in biology we've got a whole unit left, obviously. We've got one more learning outcome on the chemistry, and yet we don't finish till the end of June, so we have got time. So if this overruns a little bit, then I'm not too concerned. We can absorb a little bit of overrun. Right, the rates stuff. I'm hoping that most people's assignments are pretty much complete on that, because if you've left it to come back to now the biology's out of the way, you will find it quite difficult to remember what it was all about. All right, but the rates bit, of course, you've got all those graphs to draw. 4 graphs to draw, aren't there? The calculations to do using the Arrhenius equation, all that sort of thing. If you haven't completed that yet, then you need to get a move on with it. Theoretically, it should be due in yesterday, I think, or was it today? Oh, it's today, wasn't it? Because we were going to do the equilibrium yesterday and then the questions today. We put that off till Monday, and then I brought it back again to Thursday this week. So I want those in sort of by, well, I think Monday deadline at the latest. All right, if you can get them in before, then you know it's off your back, isn't it? And then I mark the whole lot together. I don't mark that separately from the equilibrium questions because it's one assignment. All right, so that's why I need them in together. Right, with what we've done so far on equilibrium then, we introduced this idea of the reversible reactions, where you have one reaction that we identify usually as being the one that we're studying, going from reactants to products, but in a lot of cases there are conditions where we can actually have a reverse reaction going on, but it is a matter of certain conditions, and it's conditions of things like concentrations, pressures, which is the concentration of a gas, temperature, and so on. And so what we're looking at in this section is, can we find a point at which there is an equilibrium between the forward and reverse reactions? All right, the forward reaction being sort of left to right, and then the back reaction or reverse reaction from products to reactants is essentially what we're thinking of, but right to left. We looked at some examples, you know, just breaking it down very simply, and this was actually pretty much stolen off Jim Clark's website. So this is the, we had at the beginning the hydrogen and iodine one for hydrogen iodide, and then iron and oxygen producing an iron oxide. But the fact that if you've got steam passing over the iron, then it would sweep away the product from that reaction, the hydrogen, so that it would actually keep going just in that left to right direction, because you were removing the hydrogen, so it couldn't react and go back the other way. Theoretically, however, it could do that. We looked at the idea of equilibrium being where you get the rate of a forward reaction meeting the rate of a back reaction, so that when the rates equalize, at that point the two conversions are happening at the same rate, and it looks like nothing's happening. All right, but it is still going on. It's just that both are happening at the same rate, so you don't actually see any change. I tried to demonstrate this to you and made a complete mess of it, the cobalt equilibrium. Yeah, so we'll gloss over that. You probably could find that quite nicely on YouTube somewhere, actually, the cobalt equilibrium. But yes, it wasn't playing ball for me, and I was tired, I think is the best word to use. Not that I'm a lot better now. We moved on to Le Chatelier's principle. Now, this is, it's not an explanation, it really just tells you what happens. And the principle states that if you disturb an equilibrium, then the position of equilibrium will change in order to counteract the disturbance that you've created. And that disturbance might be that you change a concentration, let's say by taking the hydrogen away in that reaction I had up on the previous bit, or you might change the temperature. There are all sorts of ways of changing conditions so that you will actually get a change in the equilibrium point to counteract that. And we're looking at concentration here. So if you increase or decrease the concentration of reactant A in that particular equilibrium up there, then the equilibrium will move in the direction that restores the equilibrium concentration. All right, so this will make more sense once we start some calculations, I hope. A similar situation applies in gases, but what you have to remember with gases is that 1 mole of a gas occupies 24 decimeter cubed. And so consequently, with that reaction we've got there, A plus 2B, we've got 2 moles of B, 1 mole of A, so we've actually got 3 moles of particles. You've only got 2 on the other side, and that will have an influence. If you push it from left to right, then it will actually reduce the pressure, whereas if you push it from right to left, it will increase the pressure because there are more particles on the left than the right. Okay, so they will create more pressure. What else did we do? Changing the temperature. I have to bear in mind here, and this is not necessarily a sort of proper way of looking at it, but you can consider heat as being either a reactant or a product. And therefore, if you change the temperature of a reaction, then are you increasing or decreasing the amount of a reactant or a product? And heat can be considered in the same sort of way. So bearing in mind that an endothermic reaction is one where the delta H is positive, you have to put heat into it. So the energy content of the chemicals rises, that's why it's positive. Then heat would count as a reactant in a way. You won't see it described like that, but it does help you understand it. Exothermic, on the other hand, where the delta H is negative and heat is being given out, it's like heat is a product. So if you heat up an exothermic reaction, you're adding more product. So it'll actually push the equilibrium back the other way. Whereas if you heat up an endothermic reaction, you're adding more reactant, so it will push it left to right. Okay. Now, for any given reversible reaction, of course, the reaction one way is endothermic and the reaction the other way is exothermic, and we know that, don't we, from energetics, that was the whole principle of Hess's law, reversing the reaction, reversing the sign, flipping the equations and the signs and all that. So, you have to use that to understand this. So, I think that's probably about it, isn't it? Did we have any more? No, we didn't. Okay. So, our starting point for this afternoon is to introduce the equilibrium constant. In the rates part of your assignment, and in the rates part of this learning outcome, we met the rate constant, K. That is a lowercase k. Go through your entire assignment before you hand it in and make sure that that is a lowercase k. You will find when you type that as the first thing on a line, of course, you'll get it auto-corrected to a capital, won't you? make sure, go through and change them. They all need, in that part of the assignment, must be lowercase k. All right. Otherwise, you are using a different symbol, really, because the equilibrium constant is also k. But this time, it's an uppercase k, and it does at least have the decency to have a subscript c. To identify it a little bit, all right, but Kc is the equilibrium constant, and that is an uppercase K. All right, this matters, and this is the sort of thing that you will lose grading on because you're using the wrong symbol. Right? You might think it's just a K. No, it is not. Now, what we have to consider here is two different sorts of equilibrium. We have what we call homogeneous and heterogeneous. And the difference between them is what sort of state or phase the items are. Whatever's in the reaction or equilibrium has all got to be the same to be homogeneous. But if there are different states or phases, then it'll be heterogeneous. So you could, for example, if we went back to some of the examples at the beginning, I had hydrogen and iodine, both gases in a flask, reacting together to produce hydrogen iodide. That's a homogeneous equilibrium. The one that followed that was iron, which was a solid, encountering steam, which was a gas. That's a heterogeneous equilibrium. And the issue that we have with that one, particularly where you've got a solid, is you can't have a concentration for solids. Solids are just solids. Solids are, you know, just all made of the same stuff, aren't they? So you know, you can't express a concentration. So yeah, that throws a bit of a spanner in the works. And the other option, of course, is gases, which yeah, you don't really talk about concentrations, particularly if it was like the steam passing over the iron. You can if they're in a container, so you've got a closed system, but you can see this, you know, it does potentially create some issues for us. So I'm just going to define these two, or I might just do them straight away. Let's do homogeneous equilibrium. This is our first one. This is the sort of thing we're going to encounter mostly. And this is just everything, reactants, products, doesn't matter, present in the same, not so much state, actually phase is a better word probably, because we don't really talk about aqueous solutions, which is where state is better. Phase is solid, liquid, gas. All right, so you might have everything as a gas or everything in the same solution. They would be aqueous then, I suppose. But, yeah. All right. Now, looking at the equilibrium constant in this sort of situation, this is more straightforward. This doesn't cause us too many problems. An example. I'm going to use examples. I think I've stolen all this from Chem Guide, but they are very common examples. The example I'm going to use here is conversion of sulfur dioxide to sulfur trioxide. And you might think, why? It's a process that's actually really important in industry. It's called the contact process. And it's part of the production of sulfuric acid. So, you know, it's part of an industrial process for producing sulfuric acid. So the contact process converting sulfur dioxide as a gas into sulfur trioxide as a gas. Once you've made sulfur trioxide, what do you think you might have to do with it to make sulfuric acid? What else does it need to become sulfuric acid? Can you remember the formula for sulfuric acid? It should come as it should be just your language of chemistry now. It's H2SO4. So what would we need to add into that to get H2SO4? Hydrogen and oxygen. In other words, water. Yeah. Right, let's have a look at this. SO2 is only going to become SO3 if we add some oxygen to it, isn't it? So, not surprisingly, it's like this. But that doesn't really balance, does it? How should we balance that? You could have half an O2. What I'm actually going to use is that. You'll see why. It's the reason why we'd try and avoid fractional balancing, although we won't always be able to, is that when we do the calculation, we're going to be looking at the concentration of reactants to the power of the numbers in front. And fractional powers are always a bit of a pain. Another example might be, oh no, I'm not going to draw that one out. Writing an expression generally, I'll come back to using this one in a minute. The expression for the constant generally we'll have to do this in bits and then put it together, really. So generally, if we want to do an expression that gives us the equilibrium constant, if we've got a reaction where you've got this sort of arrangement, and it doesn't matter how many of those you've got, A, B, C and D in uppercase are the reactants and the products. The lowercase ones are the numbers that we've used to balance, all right, the molar quantities there. We're not going to put any state symbols in this because we're talking about a homogeneous equilibrium, so they'll all be gas, or they'll all be liquid, or they'll all be aqueous, or they're not likely to be all solid. If you allow this to reach equilibrium and then measure the equilibrium concentrations, you can then calculate the equilibrium constant. And this is the tricky bit. It's finding the equilibrium concentrations from information that you're given. And I know people will make the same mistakes this year as they've made for the last, how many years I've been teaching? This is my 5th, so it'll be for the last 4 years. And the same mistake I always make when I start doing it as well, because I only do this once a year. So, you know, I have to start afresh every time. So if reaction reaches equilibrium, so it looks like nothing else is happening, and equilibrium concentrations are measured. Then we have an expression that we can use for this. Now, it's only going to be constant at a certain temperature, so you'd state the temperature. You know the reason for that, because I've said, you know, the last thing we did was talking about endothermic, exothermic reactions. If you change the temperature, you're changing, you know, the amount of heat energy, so it's going to move about. What we have is Kc uppercase K, is. Now we have the products, the right-hand side of that equation. Well, this, yeah, this is for the left to right reaction. And it's the concentration of product C to the power of its molar quantity multiplied by the concentration of D to its molar power of its molar quantity divided by, make sure I'm getting this the right way around, A times B in the same sort of format. All right. Now that works if you're finding the equilibrium constant for the forward reaction, the one that goes left to right, because the reactants are A and B, the products are C and D. If you wanted to find the equilibrium constant for the back reaction, then A and B would be your products, so they'd go on the top, and C and D would be your reactants, so they'd be on the bottom. So you sort of have to define what it is that you're calculating here. So what we've got then, yeah, I mean the indices that you've got there are literally just the numbers that you need to balance the equation. So for that example that we had with the sulfur dioxide one, the contact process, so for I've not put the gas symbols in there because I'm being lazy as much as anything else. What would be our expression? What we got on the top? Yeah, that on its own, like that. And then on the bottom we've got the to the 2. Yeah, yeah. All right, so that would be how you'd work it out. It looks quite straightforward, yeah? Right. The examples I've got on the sheets here are to do with esterification, which is the organic acids and the alcohols. And the trouble with those is it takes a long time to write out the formulae, so I'm trying to find some more straightforward ones. What you'd have to bear in mind is, you know, units that are used for concentration here. And so, you know, in terms of the units for Kc, of course, a bit like we had with the rates one, it's going to change, isn't it, depending on what you're actually putting into that. So if we did it in moles per decimeter cubed, which you can still do for gases, slightly odd, isn't it, but you can, then what would be the units? Bearing in mind concentration is always moles per decimeter cubed, what would be the units for that? What are the units for Kc if you always measure concentration in moles per decimeter cubed? In that example. Nope. It's not the same. How could it be the same? Units. So we've got on the top moles per decimeter cubed times moles per decimeter cubed, haven't we? Do we understand that? Yeah? And what do we got on the bottom? There's 3 times, yeah? Now I've set myself up to do this, haven't I? All right. Yeah. So it will do, depending on your equation. Yeah. So you've got that'll cancel out, that'll cancel out. So we're left with the rather odd that, which is, yeah, moles to the minus 1,
Yeah.
decimeters cubed, yeah. Right. This is the thing with constants, seem to have these meaningless units that are only there to balance everything out. Yeah. So yeah, rather strange, but there you go. Right, let's just use another one. Have you come across the Haber process? No? That was Born-Haber cycles. The Haber process. Have you met it in the nitrogen cycle? No? Nitrogen taken out of the air industrially to make ammonia to be used in fertilizers. Okay? Huh? Well, you're probably aware from the nitrogen cycle, it's pretty difficult to get nitrogen into living things, and yet they need it, don't they? You know, every amino acid has got an amino group containing nitrogen. Where do we get it from? Well, you've got the bacteria in the soil, haven't you? Good old, yeah, nitrogen-fixing bacteria, yeah? And you've got nitrous ammonius. Oh, I can't remember. Hate the nitrogen cycle. The only other way of making nitrogen available is to use this industrial process, the Haber process, which takes gaseous nitrogen and combines it with hydrogen to make ammonia. Your only other option is lightning. Yeah? Come across the idea of lightning actually puts a lot of nitrate into soils. Yeah? There you go. It's yeah, quite a complex thing. Right, if we were to take nitrogen and hydrogen and produce ammonia, again we've got a homogeneous reaction. I've taken gaseous ones, I could have used others. How are we going to balance that one? Yes. So this time our Kc will be what's going on the top? That's it. And then the other stuff on the bottom. So nitrogen to the power of, yeah. And then our hydrogen to the power of 3. Yeah. So we'll end up with some even more ridiculous units out of that one, won't we? All right, but we're not, not unfamiliar with that idea of having to just manipulate the units to fit, really. The units for this one, we would have, well, we've got 2 on the top, we've got 4 on the bottom, haven't we? So this time the units would be 1 over so we end up with, yeah, moles to the -2, decimeters to the 6, yeah. Very similar to the rates ones, aren't they, except that they don't involve the seconds, because we were getting that with the rates ones, except every time we were having to put seconds to the -1, because it's a rate, it's a change over time. Yeah, so these are a bit odd. Okay, let's have a look at the heterogeneous one then. I'm not sure that I give you any of these, but it's worth just making it clear that they do exist. So heterogeneous equilibrium. Or equilibria, I should probably have put. Quite a good description, bear with me. You haven't got everything in the same phase. So things, I don't like the word things, but let's say substances. Well, you've got them present in more than one phase. Okay, now you can see from what we've got up here then, if we're looking at concentrations then, it's okay with a liquid, a solution, a gas perhaps, but for a solid, if we've got a solid thrown in there, we can't have a concentration. So what happens? Well, we actually just don't include any terms for solids. So they're just left out of the calculation. And I'll give you some examples to sort of illustrate how we do this. Right. If we had, for example, steam plus red hot carbon. That you have, the steam is water as a gas, the carbon is a solid, and what we get out of that is hydrogen, quite useful, and carbon monoxide, which you wouldn't necessarily think it's useful, but it is used in, I'm trying to think, production of, is it steel? Because it helps remove the oxygen from iron oxides, doesn't it then? So you've got a mixture there of phases. You've got gas, solid, more gas. Another example, we've met some examples of reactions where you get what we call a precipitate, where you get a solid produced. If you think right back to when we were doing, oh, actually, to be honest, the one, yeah, it's only the last, you did quite a lot of reactions where you got precipitate of a solid. I've blanked the energetics out. But yeah, where you're getting a precipitate of sulfur, that is solid sulfur. So we could have that one, couldn't we? Thiosulfate. I should put sodium thiosulfate. I'm just going to put the thiosulfate and acid. And now I've actually set myself up for trying to remember what the formulae are. So you've got your S2O32 minus plus H plus. Theoretically, it could go both ways, although you only saw it going one way, obviously. What did we get? We got SO2 plus sulfur plus water out of that. There was some other stuff as well, but does that balance? No, not quite. Two of those, three of those. I just need two of those, don't I? That was all. Is that right? That's, that's not the full equation. That's missed out the sodium, and it's missed out the chloride, because you would have sodium chloride as well, but they don't really do anything, so they're not that important. But what we've got here is, well, we've got an aqueous solution for both of those. But we've got, it's a nice mess, this one, actually, because that is a gas, that is a solid, and that is a liquid. Yeah, very good example, isn't it, really? But yes, as a precipitate, and any reactions where you get precipitate, you're getting a solid. So writing the expression for Kc, the important thing here is that you don't include any term for a solid. So no term included for any solids. So if we did one for that, we would have on the top SO2 and the water, yeah. The concentration of water that's another issue altogether. And then we miss out the sulfur, and then on the bottom we've got our, and we've also got that to the power of 2. All right. Is this sort of making sense with, just getting the idea of these? All right, I think the next thing to do is to give you some examples, some calculations just involving Kc, just involving working out the equilibrium constant, and we'll see how that goes, and then we can move on from there and look at some slightly more elaborate problems. Okay, let's have a look at these then. The important thing to do is to look at what you've got to start with and see what it's actually telling you. So when a 0.218 mole sample of hydrogen iodide was heated in a flask of volume V, decimeter cubed, the following equilibrium was established at 700 K. Now the V is only put as V because we're not going to need to work out the concentration here, because you've got the same number of moles of gas on each side. You've got 2 HI on the left, you've got 1 H and 1 I2 on the right. So, they just cancel out. It only becomes important where you've got different numbers of moles or molecules on the two sides. Right, let's have a look at the first part of this then. The equilibrium mixture was found to contain 0.023 moles of hydrogen. Calculate the number of moles of iodine and the number of moles of hydrogen iodide in the equilibrium mixture. So, number of moles of iodine. Absolutely spot on, yeah. 0.023. Because you've been told you've got 0.023 moles of hydrogen. Well, this is a 1-to-1 ratio, so you must have exactly the same number of moles of iodine, mustn't you? No. No. Definitely not. This is where you're on the right track. You are on the right track. But what you've not allowed for is that there are 2 HIs. So actually, just bear with me on this. All right, so the answer here is 0.023. So has anyone got a problem with that? All right, you've got to bear in mind what these numbers mean. It's a ratio, isn't it? 2 gives 1 and 1. So 12 would give 6 and 6. 9 million would give 4.5 million and 4.5 million. Yeah? It's just a ratio. So they're equal numbers of moles of hydrogen and iodine on that right-hand side. So if you've got 0.023 of one of them, you've got 0.023 of the other one. And that was so simple you missed it. Yeah? That is easy, isn't it? That bit. The next bit, it does get harder. And this is the bit where people trip up. So this is why I left you for a little while to play with it. And I've had to write notes on my explanation of the answers because I get this wrong every time I start it. So, don't think you're stupid or anything. It's just, this is a tricky bit to start with. Right, the hydrogen iodide is here. And I could well get this wrong, and we might have to go back and rework it. Here is our hydrogen iodide. what did we start with? How much? 0.218. But some of that's reacted, hasn't it? Yeah? So we haven't got 0.218 at equilibrium. We've lost some. Yeah? Are we getting the idea? That some of it's reacted. So we want to know what's left. So it's going to be 0.218 minus something. We've got to take something away. Yes, it is. Yeah. Because 2 moles of hydrogen iodide gives you 1 mole of hydrogen, you need twice as much hydrogen iodide has reacted as hydrogen has formed, yeah? If this, we're told, where is it there? If this is 0.023, then how much of this has reacted must be twice as much, because that represents the reaction, yeah? So if 2 gives 1 plus 1, we've already worked out that we must have that. Then what must we have on this side to have reacted? There's got to be twice that, so it's got to be 0.046, hasn't it? Is that okay? That's the reaction. So if 0.046 has reacted, but we started with that, then our equilibrium concentration of hydrogen iodide, we've got to work out what's left, what's not reacted. So we're going to take away 2 lots of that. So you've got 0.218 minus 0.046. And that is where people trip up time and time again, is getting the difference between starting concentration or starting quantity and equilibrium quantity, which is what's left of the reactant. It's not what's reacted. You've got to take that away from what you started with. But we sort of getting the idea. I'm not expecting light bulbs to be going on all over the room here, but as long as you're getting the idea that these are the things you've got to work with. You'll have these as examples, you see, when you're doing the assignment part of it. So if you want to annotate and sort of, remind yourself, write all sorts of things on here to explain it, then I would do. All right. So whatever that is, which I think I make 0.172. Yeah? Okay. Now the KC bit, well, that should be doable. Yeah? Did you manage that bit, all right? So KC is on the top, we've got H2 and I2. And on the bottom, we've just got the HI, and that's, to the power 2. And then I've sort of answered the part C here, why the volume of the flask need not be known when calculating a value for Kc. And it's because you've got the same numbers of molecules, if you like, or moles on the top and on the bottom, or in the reactants and in the products. Because if we were to do, we could work it out. This is a side track. All right, so I'll do it in green because it's a side track. Where we've worked out the concentration, the amount of hydrogen and iodine, each of them is 0.23. So we could have gone 0.23. We could do it right as well, couldn't we? 0.023 over V would be the concentration, wouldn't it? That many moles in V as a volume, multiplied by 0. I was going to do it wrong again. 23 over V, and then on the bottom you'd have the hydrogen iodide, which is the 0.172. So you would have 0.172 over V, but if you square that, of course all the V's cancel out. Yeah? Right. So because you've got the same number of moles on each side, you don't need to use the volume because it just adds a value into the calculation that you don't need because it'll all cancel through. So V cancels in the KC expression. In other words, moles of products equals moles of reactants. All right, you get a lot of questions like that. That's likely to come up. I can't remember, but I'm pretty sure it's there somewhere. And so the value of Kc at 700K then? Should be able to do that. All right, it's that calculation up there, but without the V's in it, really, isn't it? So you've actually got 0.023 times 0.023, which you could have as 0.023 squared. And then on the bottom, you've got 0.172 squared, which gives you a value of any offers for that? No, not what I've got. Hang on. Make sure you're using plenty of brackets because you're dividing by, you're probably squaring something before it. That's, yeah, 0.017, I think 9 was what I'd got as a, yeah. Yeah? Okay. So here is the same reaction, but the other way round. So what do we think the value of Kc would be for this? You don't actually have to calculate it because it's actually just 1 over. To turn it the other way up, you do 1 over that. You could go through the whole thing up there. You know, it is this. If you're going to, whoops, again, it would help if I wrote it properly. 0.172 squared over the 0.023 squared, if you want, or it's 1 over 0.0179. That's how you know, do the inverse, isn't it? If you're not sure about that, you can just play around with numbers, you know, like 1 over 2 equals 0.5, and if you do 1 over 0.5, you'll find that's 2. You know, if you're not sure with mathematical manipulations like that, like say with simple algebra sometimes, you know, which do you multiply, which do you divide, put some simple numbers in that make it work, and then move them around so you can check. So what answer do we get for that? Well, I'm hoping it comes out at 50, yeah, 55.9 is what I've got. Have we got any units for that? No, no units, because we've got the same number of terms on the top as the bottom. So they just cancel out, don't they? So no units this time. All right. Yeah. Yeah, the idea, yeah, constants in chemistry, I prefer to call them fiddle factors. They're what make your your calculation work. But they are constant at a constant temperature. And it's the same with the rate constant as well. And you know, that's the second part of that assignment where you're looking at the rate constant at 2 temperatures to work out the activation energy. So it is constant for that reaction at that temperature. That if, you know, 10 different people do that reaction at that temperature, it will be a constant. But you can influence a constant, which is always odd. Because, yeah, you think of something like pi is a constant. That doesn't change with temperature. If you warm up a pie, oh, well, that's a different story altogether, isn't it? You've got dinner. Right. Okay, that's the first one. Did that make it a little bit more doable? Did it make sense then? Yeah, good. Right, now the second one I'm going to let you look at for a while, but you've got, let's just, looking at the first part of that second question, you've got acid X and ester Y, and that is simply, you know, you can call them what you like because it doesn't matter what the formula is, does it, in this at all? So you can refer to them by letters if it just makes it easier to write them down. So don't worry, the X and Y don't mean anything. They're just a shorthand version of what we got there. What is that acid? Ooh. It's, you've got 2 COOH groups. What's 4 carbons? Bute. So it's butandioic acid, I think. And then you've got methanol, so you get dimethyl. No, mut. I have no idea. Yeah, I can do that bit. Yeah, I'm not going to try and name it. I could be here all afternoon. You should be able to work that one out. I think you've got the same issue in part B there. They've put this question in a different order, but part B you've got to think about the molar units in there, if you like, you know, because you've got 1 X reacts with 2 methanols to give 1 ester and 2 water. So those are going to be important in what you're told. All right, I'm going to let you play with that for a bit before I go over it. But if we look at the ratios that we've got here, we've got 1 reacts with 2 to give 1 and 2. Now, in that reaction then, you've got a 1 to 2 ratio over this side, 1 to 2 ratio over that side. We are only told one thing, and it's this. That at equilibrium, there's 0.13 moles of Y. In other words, we've got 0.13 moles there. That 0.13 I would think of as your molar unit for this particular reaction. All right. Now, this molar unit then, if one of those has been formed from one of those, then 0.13 will be formed from 0.13. So that's how many react. All right, it's not how many are left, it's not how many you started with, it's how many react. Equally then, if your molar unit is 0.13, which we've been told here really, then this is 2 of them, so that's 0.26. And that's 0.26. Okay, and that I think is a good way to start with these, is to convert your reaction into reacting quantities. You then have a look at, what's the question? Well, the first thing is actually just to write the expression, which I don't think is particularly difficult, is it? So Kc is... Yes. Square brackets Y on its own. Square brackets H2O to the power of 2. And then on the bottom it's square brackets X, square brackets CH3OH to the power of 2. That's it. Now, calculating the number of moles then, unfortunately I'm running out of space here, of X, the number of moles of methanol and the number of moles of water. Right, well, X, we were told that we started with 0.25. We haven't got that anymore because, which one we're looking at? I've lost it, X. 0.13 has reacted. So we are left with, that's it, 0.25 is what we started with. We've worked out that 0.13 reacted, so we're left with 0.12. You can put 0.12, but you've got to think about how I grade. All right, so if you are showing your understanding and all that sort of thing, in an assignment that's fairly straightforward, it's about explanations. But the same thing can apply here, can't it? You know, you can just randomly choose a number, couldn't you? And be lucky. Moles of methanol in the equilibrium mixture is? That's correct. Yep, we started with 0. Whoops. Seems to be a lot of whoopses. 0.34. And our equation tells us that 2 of the molar units reacted, so that was 0.26. And that gives us that, I believe. Is that right? 2 zeros and an 8? No. Why 2 zeros, you silly woman? No, the 0.34 is just what you've been given. You're literally given, you are only provided with 0.34 moles at the beginning. You can't, yeah, the 2 is already in there. But that 0.34 is not part of the equation at all. That's just what you were given in a bucket. You know, that's not the reacting quantity. And the moles of water, yeah. I'd be tempted to, you know, if you're going to explain it, put it in like that. All right, the problem can be these numbers, the 0.25 and the 0.34, that they confuse matters. They don't react. They aren't there at the equilibrium point. They are, you know, what you're given to start with. They're both more than you need. They are excess quantities. So, yeah, you've got to separate your starting volumes, your reacting volumes, and your equilibrium volumes from each other. Not volumes, quantities, sorry. Starting quantities, reacting quantities, and equilibrium quantities. An equilibrium quantity is the starting quantity minus the reacting quantity. I think, yes. Now, the next bit is exactly the same as before. Why don't we need to know the volume? Same, that's it. Moles of reactants are the same as the moles of products. You've got 3 on each side, I think, haven't you? 1 and 2, 1 and 2, so moles of reactants equals moles of products. And the other alternative way is V cancels out in the Kc expression. You know, it's they are saying the same thing, really. And right, have we got a calculation for that yet?
Well, we have a sort of think we've got a 0.13 times 0.26 compared to
0.13. 0. Okay, 0.13 over 0.26 squared, and on the bottom,
0.18.
yeah,
So 0.08.
0.08 squared, yeah.
Equals 11.
It certainly does equal 11.4. Okay, and then anybody else like to tell me the units? None, exactly, yeah. No units. They cancel out. I mean, we've said in part C that the top and bottom cancel out, don't they, in terms of how many times they're there. So, yeah, if you've got same on the same number of multiplications on the top as on the bottom, so there aren't any. So why you are left 2 lines to write the word none, I don't know. But yeah. All right. Well, while you've got that in your mind, I'm just going to move on with the idea of how Le Chatelier's principle can be applied here. I've got some other handouts which just provide some more notes, really, which I'll give you those at the end, actually. The next bit, then, is to think back about Le Chatelier's principle is just telling us that if you disturb an equilibrium, perhaps by adding some more product or taking away some product or raising or lowering the temperature or adding a reactant or that sort of thing, the position of equilibrium will change to actually counteract what you've done to it. The effect of changing conditions. So Le Chatelier's principle and the equilibrium constant. All right, that's my shorthand version of it. We've got to consider these various things. First of all, if you change concentrations, then what you've got, the important bit is, let's have a look, the facts that you've got here. Equilibrium constants aren't changed if you change the concentrations of things, I hate the word things, that are present in the equilibrium. So the concentrations won't change the equilibrium constants, and it does tell you that the only thing that changes an equilibrium constant is a changed temperature. Obviously, if you change concentrations, you'll change the position of equilibrium, but that doesn't change the equilibrium constant. Hence, it is fairly constant, right? So, no effect. All right, and you will eventually have a set of notes that sort of takes you through this and explains it a little bit more. But I just want to go through quickly and pick out the important bits of this. If you've got the change in pressure, which is sort of the same, really, because for gases, you know, that's what pressure is, it's concentration. It tells you there, the fact, equilibrium constants aren't changed if you change the pressure of the system. The only thing that changes an equilibrium constant is a change of temperature. You might notice he's trying to make a point here. And this is where I'm going with this. Okay, this is on the equilibrium constant. It's not about the position of equilibrium. If you were to add a catalyst, I'm jumping to the end. No effect on the equilibrium constant. This is a deeply meaningful bit here, isn't it? However, of course, that leaves us with the bit in the middle or near the end, changing temperature. you will get, constancy at one temperature, but change the temperature. And he's given you there KC or KP. Now, the difference there is KC is actually, the little c means concentration. It's rather like with the rates. We did rates with, the changes to do with concentration and then temperature. But with this one, you've got KC or KP. The C is concentration. What do you think P is? Pressure. Yeah, because it's just the same version, but for gases. So they are constant at constant temperature, but they vary as the temperature changes. And you've got a couple of examples, or an example there, to do with that hydrogen iodide expression. And the two values quite different. The constants are 160 at 500K and 54 at 700K. All right, so the constant is lower at the higher temperature. So what does that mean about the actual expression? Trying to explain here. Your expression has got reactants on the top, and no, it hasn't. It's got products on the top, reactants on the bottom. If that Kc value gets smaller, it means that those values on the top and bottom have changed, doesn't it? It means that the number on the top has got bigger, or the bottom has got smaller. Yeah, to make the overall one smaller. And that's an exothermic reaction. If you look at the top there, it tells you that the delta H is minus 10.4 kilojoules per mole. So if you heat it up, you would actually expect it to be going backwards and making more reactants rather than product. I saw that go whoosh. So yeah, that didn't go in, I don't think. So temperature does affect. All right, so yeah, we're going to come back to that. I'm going to go and collect the versions of this that I want you to have now. I think I would give those to the bin. All right, unless you've got one which is, I think it was 6 sides, then yeah, I'm going to stop at that point.